Let's take a look at a brief history of artificial neural network. In 1940, late 1940, there has been a major emergence of digital computers, and it was enormous effect. Okay, in 1950, late 1950, I think it's 1958 or something. Rosenblatt proposed a first prototype of neural network, which is called the perceptron. At the time, actually, the application was some gate function in digital circuit, and or exclusive or complement. And he introduced this activation function, which is a nonlinear type of function, some kind of mapping, and without this activation function, Professor Bernard Widrow, he proposed ADA-line, adaptive linear combiner, or adaptive linear element. And with ADA-line, it's much more easier to deal with this neural network in mathematical analysis. But we have some stagnation period. This is first stagnation period from 1969 to early 1980s. There was some kind of serious problem in the single layer perceptron, which is called the exclusive OR problem. So in his book, this monograph, Perceptron, in 1969, Marinescu and Seymour Papert, they proposed with a single layer perceptron, you cannot even solve an exclusive problem. Okay? But we have a turning point in 1986. There has been a multi-layer perceptron, which actually solved the exclusive problem. So in Lomenhart and McClelland, they solved with this multi-layer concept. With multi-layer in the monograph, parallel distributed processing, volume number 1, 2. Okay. So there has been a breakthrough by using multi-layer perceptron, but at the time it was a single. This is nothing but a toy problem because we don't have enough data. Maybe less than 1,000, more than 100. Okay, and it is called a toy problem. Okay, and but actually, at the time we have some kind of hope that it maybe solve some complex problem in this AI community. So in 1990, they developed hardware, analog of VLSI, or optical neural networks. And they developed digital hardware for this made structures of network structures of this artificial neural network. Okay. Of course, there are second stagnation period because as the hidden layer, number of hidden layer goes deep. Okay, we have many layers, deep neural network. Then we have a problem with adaptation of those weight parameters. Okay, that was the second stagnation period. But in 2015 or 2016, Professor Hinton, their team developed some kind of nice deep neural network actually solved a very complex benchmark problem. In machine learning, why we are using neural networks? On the right hand side you can see input and hidden layer and upper layer. Actually there are 2 layers of processing elements inside. Okay. Actually the input layer, they just in the input layer we have this data distributed over. Okay, we have a powerful learning scheme developed, which is called backpropagation. Later, you are going to have experience with this algorithm, and we can do learning by experience, example, and experiment. Okay, without any model, without any mathematical model, you can solve some complex problems. Okay, usually classification problem and identification problem of object have been performed. Okay, of course, face recognition problem and voice recognition problem, etc. And also you can do with appropriate hardware. You can do fast parallel operation and ideally light speed because you can use optical neural network. And also we have advantage of potential intelligence. Intelligence means not like just like a human, similar to human. So human has some kind of tolerance. In order to say, in other words, we have some plan B, for example. We are not going the optimum track. Okay, we are not following the optimum solution sometimes. Of course, the optimum solution is the best one, maybe, but sometimes we can do that because of uncertainty and some complexity. So in that case, we have second choice or plan B. That's intelligence. Okay? And we have numerous general purpose applications. Okay? I'm not going to list up the whole applications we have done so far. Okay, neural network definition. Neural networks are a class of interconnected devices consisting of a processing element. I'm going to use PE as abbreviation. And processing units, or we may say node, just node, which are connected with one another by connection strength or weight. These are all parameters we can deal with. Where patterns or numerical data are trained and stored, we are storing the information of these weight parameters. And these weights are numerical values, just numerical values for neural networks to learn and store. Okay, so here we have a hidden layer and outer layer, input layer. The numerical values to be stored in memory called weight, or we may say just parameters. Okay, here, adaptation means learning by example or experiments. Okay, so as we learn, find the appropriate solution. In order to find the appropriate solution, we change the weight W, IJ, or WKJ, etc. In order to come up with this intelligent solution. Alright, let's take a look at an example. A complex visual pattern recognition problem where we have a dalmatian, a dog, lies in the flower garden and try to find it with a camera attached notebook. Okay, here we have a dalmatian, but we have a foreground as dalmatian, but in the background we have a bunch of flowers, okay, blooming, and the trees, and in the sky we have a cloud. So how can you know, okay, as a human, you know which one is the dalmatian, but the computer will not recognize where it is or what is it. Okay, so the solution in this pattern recognition program will first select regions of interest somehow, and second classify and make groups in the image. That means we are going to have some kind of segmentation problem, blob. Okay. Third, find the noise-free edges by collecting lines. Maybe we may use edge detection, okay, in order to distinguish between the background and foreground, which is this dimension. Number four, we need to analyze the meaningful edges by the relational properties of the target's template. And finally, number five, we distinguish the target from the background textures. That's what it is. What this neural network does in this recognition problem. Okay. Okay, let's compare between digital computers and biological neural networks. Okay. The speed of a computer is 10 to the 7 times faster than 10 million times faster than that of a biological neural network. With biological neural network, maybe some millisecond or microsecond. But the former, the 4-nanometer computer, proceeds sequentially, okay, while a neural network is massive, parallel, and they are interconnected between nodes. Okay, and therefore with only 0.1 millisecond response time. Okay? So the latter is able to compute and solve the previous pattern recognition problem within 100 milliseconds if possible. Okay? So here we have on your left hand side we have typical motor neuron, and inside this neuron we have inside the cell we have mitochondria, axon, synapse, dendrite, etc. So we have a massive parallelism interconnection, connectivity, can deal with complex problems. So we model the left-hand side biological neuron into the right-hand side multi-layer perceptron. Okay, we have another example, character recognition. This is a pattern matching program, and we can compare with handwritten and typed characters, and it may be idiosyncratic and different. Also, we can rotate, scaling, and tilting because we have handwritten characters. And sometimes we have a priori information which helps, okay? That is to say, the order and direction, where it starts and where it ends, okay? So we have this black box. Of course, we have this circle, but this is trained memory. And we have some A character comes in, handwritten character, then we can decide this is the character A, okay? That's a pattern matching problem. So we have this example of character recognition, a simple pattern recognition with the characters. Let's say we have a pixel size. This is from the fax machine, for example, and the pixel size is 5 by 7, 35 pixels inside. We need to convert to a row vector. So only black and white stuff. So if white is 0 and black is 1, then we, in row direction, we decompose each row, connect together, and come up with a vector with 35 nodes or ranks. Of course, 35. We have a neural network with multi-layers. So we have node, which is processing element, and we have connection strength, which is weight parameters. Okay? So here we have input, hidden layer, and output layer. Okay? So you train this neural network by using artificial neural network, and we have learning mode. Okay? So data comes, the input is coming in, the output, we know the output. This is character A, so we know this ASCII code. Okay? And after that, after you train this network, if something similar to A comes in as an input, then we can come up with the output saying that this is the character A. Okay? I think we better take a look at Hebbian learning, which is unsupervised type of learning. So Hebb, in 1949, in his book Organization of Behavior, he said biological neural systems are not inborn with knowledge and ability as a sequel from the very beginning. Okay, so it actually, we have a learning system incorporated. So here we have this Pavlov's conditioned response. Okay? In Pavlov conditioned response, we have a sight of food and sound of food. Okay? We have a food, actual food. At the same time, we have a sound, a bell, for example. Then this dog learn, okay, I'm hungry, and as I eat this food, dog food, I hear the sound. Okay, so as time passes with the learning process, this dog learns that as we have this bell sound, then he has his saliva out of his mouth. Okay? So if the neuron of if the axon of a neuron A has enough stimuli to neuron B and is fired repeatedly, okay, and continually, then a growth process or metabolism occurs to either one or both neurons. And the efficiency of the neuron C firing neuron B eventually increases. So that means the sound of food to the salivation signal, okay, saliva, okay. So C, between C and B, we have a weight connection, and the strength of this weight is increasing as the learning process, repeated learning process of the stimuli. So even sometimes if you cut off this connection between A and B, also we have this weight, okay, connection, strength is higher. Even if we cut off this connection between A and B, only the sound of food between C and B, it actually produces the dog's saliva. Okay, so he actually hear the bell, and we have a salivation signal from the mouth of this dog. Okay, this is what it is. In Pavlov's conditioned response, we cut off the connection between A and B, and because we have repeated the learning process between C and B, we have a huge connection strength. This is not weak. So the weight efficiency in the axon of neuron C, which is enough to fire neuron B, which is salivation signal. So Hibbs' assumption says the excitation of neuron A has enough stimulus for neuron B, but that of the neuron C does not have. Now, with the learning process with the neuron A, the connection strength of neuron C increases, and eventually without neuron A, neuron B can be excited by neuron C only. That's what it is. Okay, now this is general processing unit, PE, processing element, or node, or unit. Okay, so we have many dendrites possible. So we have many input from x1 to xn. Okay, inside the neuron we have mathematically we have a sum product. Net J equals to summation J W ij x I. Or you can change that net I, which is summation J W Ji x xj. Okay, so this is the i's processing element. So the output is I, so the subscript index is I. So you can come up with a net I numerical value, and we have activation function small fi, which is nonlinear, and then the output is OI. So output is only one axon allowed. Okay. The net input of i's processing element is net I, which is just some product. J starts from 1 to n, wij, xj. And then we have a connection strength, which is weight. I told you this is the parameters. Okay. So wij is excitatory if wij is greater than 0. And inhibitory if wij is negative. Okay. And then we have activation value. AIT is small fi or big fi. AIT minus 1, comma, net IT if it is discrete. And we have some differential equation, dAIT dt. Which is a small f or big F, I, AIT, net IT. So AIT is the state, actually output of this expansion function, and net IT is the input. So in this case, this is continuous iteration. So therefore, we have an output value, YIT or OIT is small fi AT, AIT. So YIT or OIT is small fi net IT if AI is net I. Okay? Next thing we have this elementary stuff. So in this general processing elements, the mathematical model of neural network is a dynamic system which evolves with time. That means parameter, weight parameters or bias, those parameters are changing with time. As we have learning process, as we have training procedure going on and on, this W, the weight parameters changes and updated. Okay. We have a learning rule because we have synaptic connection strengths, and this is updated as some learning process proceeds, so that neural network may store data of weight, which are actually numerically encoded to learn what to do. So here we have a new wij is from our learning algorithm, and this old wij is changing, updated. Of course, we have xj and yi input and output, and we also have vector notation. So you can use n-dimensional input for xj, x, for example. Boldface x is our vector notation, and weight for wij is boldface wi. This is another vector, so with the same dimension. So I want to make sure that the number of input is the same as the number of weight attached to each input to the processing element. Okay, same dimension between input and the weight to the weight vector to the processing element. And as output, we have m-dimensional output units for the net I and boldface net means our output of this processing element. Okay, so here we have net I, which is some product j start from 1 to n, wij, xj. Or you can just simply write boldface wi inner product boldface x, which is the same as boldface wi transpose boldface x, because this is just inner product between input and the parameter, weight parameter. Okay,